The final video for today's class is going to be a practice problem that blends what we've been learning in phase equilibria with a type of problem that you may see in separation and mass transfer operations. As I've said before, these are my favorite type of problems. This one says you desire to separate 10 moles per second of an equimolar liquid mixture of 1-butene and N-heptane at 100 kilopascals and 0 degrees Celsius. The flash drum operates at 50 kilopascals and 0 degrees Celsius. Predict the exiting flow rates and compositions of the vapor and liquid streams. Assume that deviations from ideal behavior are well described by the van Laar equation with van der Waals parameters. The first step to solving this problem is to draw a process flow diagram similar to how you did in material and energy balances. Why don't you pause the video now and try to draw your own such diagram? Well, what are you waiting for? Why haven't you paused the video yet? Pause the video and try to draw your own diagram. Okay, fine. I'm going to stop messing around now and I'll draw the diagram. Okay, here we go. This is what your diagram should look like. All information from the problem statement in prose form has been converted into a diagram with arrows and boxes. This might have been unclear from the problem statement, but the 100 kilopascal 0 degrees Celsius is the temperature and pressure of the inlet stream. And at this relatively high pressure, 100 kilopascals is about atmospheric. And this is a low temperature, but when I drop the pressure, this is what a flash separation is called. When I drop the pressure on a liquid stream, I induce some of it to vaporize, and that's where we're getting what we assume to be vapor-liquid equilibrium. Now, we don't know for sure that this system is going to be in phase equilibrium at this temperature and pressure, but I'll assume that it is, and if I get a strange answer for the liquid or the vapor flow rate, then I'll know something is wrong. So just like we did in material and energy balances, the next step is to perform a degree of freedom analysis on this process flow diagram. Remember how much fun these were? So all I'm doing is I'm counting the number of unknowns. And in this example, I've got V dot is what I'm calling my flow rate of the vapor stream. That's one unknown. The mole fraction of 1-butene in the vapor stream is a second unknown. I'm going to choose to account for the mole fraction of heptane in this stream as not an unknown. So I'm just going to call this mole fraction 1 minus Y-butene to simplify things a little bit. So instead of counting 3 unknowns here, I'm just going to write it in terms of an unknown that we already have. L dot is the flow rate of the liquid stream. That's unknown number 3. And the composition of the bottoms stream is our 4th unknown, where I'm doing the same thing. I've omitted saying that X1 of heptane is 1 minus X1 butene. All right, so I have 4 unknowns labeled in the diagram now. How many material balances do I have for this system? Well, remember from material and energy balances that you can write one material balance for each component in the system. So because this is a binary system of butene and heptane, I have 2 material balances. How many other equations do I have? If I perform Gibbs phase rule on this system, it's 2 plus components minus phases. So if I assume that there are 2 phases, it's 2 plus 2 minus 2 is equal to 2. I have 2 independent variables that I must set. And because I have temperature and pressure already set in the problem statement, I have Gibbs phase rule satisfied. So because each component must be in phase equilibrium, I have 2 relationships, which are the phase equilibrium relationships. Next, I need to obtain what the equations are for these phase equilibrium relationships. If this were an ideal system, these would be the 2 Raoult's laws. However, it's not an ideal system. The problem tells me that it's non-ideal, however, it does obey the van Laar equation of state. So instead of Raoult's law, I can write my modified Raoult's laws in terms of the variables that I already know. So why don't I go ahead and write all 4, see if you can write the 4 equations. So write the 2 material balances and then write the 2 phase equilibrium relationships. All right, here are my 4 equations that I'm going to use to solve for the 4 unknowns of the problem. First, I have 2 material balances. So I have the overall balance and a butene balance is the second equation. The third equation is the phase equilibrium relationship for 1-butene, and the second equation is the phase equilibrium relationship for N-heptane. Notice I have the same 4 unknown variables in each of the equations. However, I also have some other variables that I don't have numerical numbers for yet. So P1 star is the vapor pressure for 1-butene, so I need to obtain what the value is for that. Since I know what the temperature is, however, I'm just going to use Antoine's equation to calculate it. Same thing for P star 2. Also, I need to figure out what to do with gamma 1 and gamma 2. Remember, these obey the Van Laar equations, so I'm going to write the Van Laar equations such that I have them handy. Recall that by the Van Laar model, these are how our activity coefficients are defined. The parameters in this case is L12 and L21, which are functions of the van der Waals parameters A and B, which in turn are functions of the critical temperature and critical pressure. So I'm going to clip and snip all of this information into Microsoft Excel, and then I'm going to use that as my calculator to proceed from here. Okay, we have some numbers to crunch. I'm going to make my life a little bit easier and assign clearly my component 1 and my component 2. So I'm going to call component 1 my N-butene, 1-butene, and component 2 is going to be my N-heptane. All right, what should we calculate first? Why don't we get the vapor pressures first? So let's say P1 star at 0 degrees C and P star 2 at 0 degrees C. All right, so for this, I'm going to need the Antoine's parameters. So I'm going to need to look up A, B, and C. Where should I go to look those up? Let's see if they are in Felder-Rousseau and Bullard, one of my favorite textbooks. So I have the E version of this. Actually, while I'm here, this is table B1. I know for a fact that these are in table B1. So 1-butene is what I'm going to need, one of them. The critical temperature, which I'm going to need later, is 419.6. Critical pressure is 39.7. I'm just inputting stuff into Excel. Let's look up the same thing for N-heptane. Scroll, scroll, scroll till I get to N-heptane. And in this book, the N doesn't count alphabetically. I think this column is my TC. So 540.2 Kelvin and 27. 540.2 and 27 atmospheres. All right, let's continue to look in table B4, which is where the Antoine's constants are. Hopefully I've got both of them here. So 1-butene is, let's see, we're slightly outside the range. So I have a decision to make. Either I'm gonna have to look up another version of the table for the Antoine's coefficients, or I can say that minus 3.7 degrees C is close enough to 0. I'm going to give it a look and see if they're in the NIST webbook, and if not, I'll use these values just because we don't have anything else. But I will try to see if I can get the correct values. And then for N-heptane, we're outside the range again, so I'm going to have to do the same for N-heptane. And I just noticed that I wasn't sharing my screen for the Felder-Rousseau and Bullard book. This is what I was talking about. So for 1-butene, my range of degrees Celsius goes from minus 77.5 to minus 3.7. So 0 degrees C is not included. So 4 degrees C isn't really a huge problem. I could probably extrapolate this without too much error, but I think 26 degrees might be a little bit too much for N-heptane. So I'm going to have to use a different resource and look on the NIST webbook. If you're curious about what table I was looking at to get the other values, that's in table B1. So in table B1, you've got the critical temperature and critical pressure for many compounds. And heptane is right there, 540.2 Kelvin, 27 atmospheres. And 1-butene was 419.6 and 39.7. Okay, interestingly, NIST struck out too. NIST has the same data range as the Felder-Rousseau and Bullard textbook did, but luckily I do have a third resource. I'm looking up in the Dom and Visco textbook, which I do not have the electronic version of. This is Appendix E of that textbook, and I'm looking up 1-butene is listed from minus 82C to 13C, so I am within that temperature range. So I'm just going to briefly input all that data into my Excel file. All right, so to calculate the vapor pressures now, let's see, this table gives me the log-based version, and T is supposed to be in Celsius, and it's going to give me the pressure in millimeters of mercury. So I'm going to say equals 10 to the power of A minus B divided by C, because T is 0 in this case. So I'm not going to need any more parentheses than that. That is going to give me my answer in mmHg, and then if I copy this cell down, it takes the correct cells. Next, I want to convert this to kilopascals. So I know this is millimeters of mercury. If I convert this to atmospheres, I need to divide by 760. And then to convert to kilopascals, that is what, dividing by 100 again. No, multiplying by 100. 101.325 to be exact, equals this cell times 101.325 divided by 760. This gives me my answer in kilopascals. Let me just make another heading here just so that I'm keeping my data straight. Okay, now I've got the vapor pressure in kilopascals, which is important because my problem gave me the pressure in kilopascals, so I want to be consistent with my units. Next, I need the Van Laar model, so I'm going to bring this over here and make sure I don't make a mistake. So where do I want to do this? Let's keep going right to the right. So A constant and B constant. So A1 is going to be, I'm going to need the gas constant R. This is part of the fun about using Excel, is you can really array your spreadsheet however you want. R is going to be equal to, what do I want the units of the gas of R to be? I've got K atmospheres, K in atmospheres per mole, right? So let's do 8.314, and that is going to be in pascals, meters cubed per mole Kelvin. Remember, it may be tedious to write these units out like this, but if you always think about what your units are, you'll save yourself a lot of headache when you have a mistake with your units. Let's see, does this have to be in any specific, what are the units of the A and B constant going to be? Should both be in terms of volume, right? Because you got temperature, pressure, so the temperature is canceling in the R, the pressure is canceling with the R, meters cubed per mole, so it's going to be in terms of molar volume. So equals 27 times R squared, I'm going to $sign it, times critical temperature square, not going to $sign that one, divided by 64 divided by critical pressure. Sorry about that, I was just working out the units myself. The units for A are actually pascals meters to the 6 per mole squared. Now it's not going to matter because when we plug them into the, when we plug the A and B into this expression for L1 and L21 and L12, all the units cancel anyway, and these parameters are dimensionless. So I encourage you to try that out on your own. Verify for yourself that all the units cancel out. And as long as I'm consistent, it should not matter what value of the gas constant I choose or what my units are. So I'm going to drag this same thing down for A, make sure that I'm choosing all the cells that I need. And it looks like I am. And now I need to calculate B. So B is equals R, $signed, times TC divided by 8 divided by PC. And drag that down. Okay, now let's calculate L12 and L21. I love using Excel as my calculator. Let's see, do I want to, yeah, I want to keep the same value for R here. So I want to say L12 is equals B1, I'm going to put this in parentheses, make it very difficult to mess up. So B1 divided by R times T, and T in this case is 273 Kelvin, right? So multiply that by square root of A, square root of A1 divided by B1 minus square root of A2 divided by B2. Close that, close the big parentheses, and square it. Okay. So instead of doing it again, oh, I'm going to have to do it again, aren't I? Oh, maybe not. Did it keep it correctly? So, no, it did not. I'm just going to do it again. So L21 is B2. B2 divided by R divided by T times square root of A1 G8 minus, divided by B1. Oh, so that part is correct. Oh no, did I mess it up? I think I did. I think I should not have moved. L21 is B1, cell H8. And L21 should be cell H9. Ah, that's what the problem is. Okay. I had the wrong formula highlighted. I need to drag all these up one. All right, how does that look? No, it shouldn't be the same answer. This should be H8 because that's got to be B2 divided by RT there. Okay, they're at least different now. Oh, I should kick myself. I always tell you not to make these type of mistakes, and I made the type of mistake myself. Do you see where I went wrong? It's a unit problem. Where did I have a unit problem? Try to pause and see if you can highlight which unit I messed up. It is that PC is in atmospheres, and it must be in pascals if I want to use this value of the gas constant. So instead of atmospheres, I want to say this is equal 101,325 times atmospheres. And I want to say this is equals 101,325 times atmospheres. Now I'm going to change the heading to pascals. All right, just going to double check everything once more. Nope, so one more mistake. Good thing I'm looking this over. I square rooted a quantity instead of just the A parameter there. And I did the same thing here. All right, one more once over. Okay, I think it looks good now. I debate whether or not I should go through and have the Excel spreadsheet all ready for you when the video comes, but I think it's very informative if I do it the first time and you kind of see if I make the same mistakes that you're likely to make, how I go about thinking about it and fixing them. So I think I've got everything under control now. I've got the right values for the parameters. Next thing to do is to calculate the values of the activity coefficients. So I'm just going to keep going, gamma 1 and gamma 2. Now I don't need to do a column like I usually do because I'm not interested in more than one temperature and pressure. There's only one temperature and pressure of interest here. So gamma 1 is equal to exponent of L12 divided by the quantity 1 plus L21 divided by, no, L12 divided by L21 times x1 divided by x2. Okay, so here's an interesting part. I don't know what x1 and x2 are quite yet. So I have to write it into Excel somehow. So I'm going to stop doing this formula. And I'm getting into modeling the whole thing now. So I'm going to need, my four unknowns are going to be V, L, this is V dot, L dot, Y1 and X1. All right, so maybe you can already see, but I'm going to need the use of solver in order to solve this system of 4 equations, 4 unknowns. Right, because gamma depends on x. What I could do is I could plug in the Van Laar equation, I could plug this thing in for gamma 1 and plug this thing in for gamma 2 and try to crunch through this algebraically to solve for x1, but that does not look like fun. So I'm going to give an initial guess for all of these. So I'm just going to say 5, 5, and then for y1, I don't know, 0.75, for x1, 0.45. All right, these are just initial guesses once again, and initial guesses to be used as placeholders in calculating everything for when I use solver later. So here, oh, where did I leave off with parentheses? 1 plus, right there, right? So multiply that by x1, which is there, divided by 1 minus x1, because that's x2. All right, so close that out, close the purple ones out, close the red one out, and that is squared on the bottom, and close out the exponent. Okay, that's gamma 1. Okay, it's close to 1, but not exactly 1. That is a good sign. Let me see if I can copy this down. Do I want to copy it down? No, I want to type it all in fresh so that I'm certain that I'm not going to make a mistake. So it is exponent L21 divided by open parentheses 1 plus L21 divided by L12 times quantity x2 is 1 minus x1 divided by x1. Close purple, close red, square. Okay, perfect. We got 2 activity coefficients that are almost not quite 1. That is a good sign, right? I know the activity coefficient should be between 1 and 5. And the fact that it's 1 means it's almost ideal, but not quite. And I've got butene and heptane, which are similar-ish molecules. Butene just has a double bond. Heptane is a straight chain carbon. All right, now what? I've got everything I need. The only thing I need to do now is in Excel, I need to model my 4 equations and 4 unknowns. So how do I go about doing that? So I'm going to do the trick where I bring everything over to the other side. So I'm going to try to goal seek all of these equal to 0. So in other words, equation 1 is my material balance overall. So I'm going to say that is equal to 10 minus V dot minus L dot. And I picked numbers such that it's equal to 0 already, but this is going to be one of my constraints, right? I want all these equations to equal 0. So equation 2 is equals 5 minus y1 times v dot minus x1 times L dot. That one's obviously, this is not 0. So the fact that it's not 0 tells me that this guess that I pulled from out of nowhere is not correct, but I'm going to use solver again to fix it, so it's okay. Equation 3 and equation 4 are my 2 Raoult's laws, modified Raoult's laws. So I'm going to bring everything over to the other side. So equals y1 times, let's see, do I want 50 kilopascals? Do I want it in kilopascals? Yeah, I want kilopascals. Times 50 minus gamma 1 times x1 times the vapor pressure, which in kilopascals is this one. Okay, and same thing for equation 4. So equals 1 minus y1 times 50 minus gamma 2. Did I put gamma 1? I can't remember if I put gamma 1 in the last one. I'll check that. 1 minus x1 and times p star 2. That should all be equaling 0. I put yeah, I did put gamma 1. Okay, I thought I was forgetting things for a moment. All right, data solver. Objective must be a single cell. I didn't put anything yet. Okay. Huh. I wonder what that was about. Okay, so my objective, I'm going to set it to be equation 1 to be value of 0 by changing variable cells of my 4 variables, subject to the constraints that these 3 must all equal 0. Okay, and do not make unconstrained variables non-negative. Crunch it solver. All right, so it's got all of my equations roughly equaling 0, which is good because I brought everything over to the other side. Let's see what values I end up obtaining. Okay, so this tells me that about 25% of the mixture vaporizes. So I've got 2.4 moles per second that is vaporizing, and the composition is going to be primarily my component 1. So 97.9 or 98%, if we're rounding, of 1-butene, and about 35% 1-butene remaining in the bottoms. So if I wanted to answer the question of predicting the exiting flow rates, the vapor stream flows at 2.42 moles per second. Composition is 98% 1-butene and 2% N-heptane. And the liquid stream is 7.58 moles per second. Composition is 34.7% 1-butene, and the balance, let's see, quick math, 65.3% N-heptane. All right, so that is the solution to that problem. This should be good practice in not only practicing using the Van Laar equation, but also practice in using Solver with Excel, and also how to array your Excel spreadsheet to keep everything straight in your mind. Hopefully the mistakes that you saw me make are informative as well to help you out with when you're troubleshooting Excel. What are the type of things you need to be looking at, and how are you double checking to make sure your work is correct? So that's all for this video. Thanks for watching.